Do you still believe primes are completely random? Ironically, we already have a powerful tool that predicts the number of primes with surprising accuracy. It is LIVX, a function proposed by Gauss. But unlike the actual number of primes, LIX is smooth, so the gap between them grows and shrinks. It wriggles almost like a wave. Why does this happen? Why is LIVX so jagged? Riemann finally uncovered the answer through the zeta function. In an instant, primes became waves. Riemann revealed the source of those waves. The third leap begins with JUX, Riemann's prime counting function. LIX gives the smooth and average shape of the prime distribution. Log2 is a constant. This term becomes extremely small when x is large. So the real mystery is the second term, which is the main correction term. Here, rho represents a special kind of complex number, a non-trivial zero. So this term is the sum over non-trivial zeros. Then, what does a non-trivial zero actually do? To make this concrete, let's actually calculate JUX. X equals 1 million. Let's take the very first non-trivial zero, rho 1. First, compute x to the rho 1. Use Euler's formula. This is x to the rho 1. Plug this into Li of x to the rho. When rho is complex, Li value behaves roughly like this. So this is Li value for rho 1. But something unexpected happens. Why is this still a complex number? Now we are trying to count primes using JUX. So shouldn't the answer be real? The reason is simple. We haven't included the conjugate zero yet. Non-trivial zeros come in conjugate pairs. So together with this zero, there's also this conjugate zero. For this conjugate zero, the corresponding x to the rho and Li value are like this. We add the two Li values. The imaginary parts cancel, so the first zero pair contributes about 5.219. Put this into Riemann's formula. This is J of 1 million when we include only the first non-trivial zero pair. Compare this with the actual number of primes. The error is now about 123. The value of LIX is this. So even the first zero pair already improves the approximation. Now let's add 3 more zeros. Their corresponding values of x to the rho and Li values are approximately like this. Again, we include each conjugate zero as well. So the final contributions are twice the real part. Let's see what happens to J of 1 million. Include 0 zero pairs. Include 1 zero pair, 2 zero pairs, 3 zero pairs. Include even more zero pairs. Then the picture becomes clearer. Its value gradually gets closer to the actual value. Notice something important. Adding more zero pairs does not make the estimate improve in a straight line. Some zero pairs pull the estimate downward. Others push it back upward. The value behaves like a wave. Some waves reinforce each other. Some waves cancel each other out. So here's the key takeaway. A non-trivial zero rho equals beta plus I gamma. The Li value for this zero is complex, but when this zero is paired with its conjugate, the imaginary parts cancel. Only the real contribution remains. That real part behaves roughly like a cosine wave. So the main correction term in J of x is the sum of all these wave-like contributions. It corrects the smooth approximation Li of x and brings it closer to the jagged pi of x. Look at the graph of Jx as the number of zero pairs increases. It ripples like a wave. This is Riemann's third leap. One zero corresponds to one wave. The dance of countless waves determines the distribution of primes. In that sense, primes are waves. The source of those waves are the special complex numbers called non-trivial zeros. This leads to the crucial question: what if all non-trivial zeros share the same real part, 1/2? This statement is the Riemann hypothesis. What happens to primes if every zero has the same real part, 1/2?